Hello, thank you for joining my YouTube channel. Today we are going to cover a topic on mechanics of solid, and we're going to look at elongation due to self-weight. So in this example, I have a body that is suspended and this is a fixed place. So I'm going to start by drawing the free body diagram of this sketch. So the free body diagram, I shall have that. So at the top we have a stress force. It is pointing upwards, it's being held upwards, and here at the bottom we have weight due to gravitational force. So we're going to use these two forces to analyze it. So firstly, we're going to look at the stress force at a distance y. The stress force, so we know that stress is given by force divided by area. Therefore, force will be given by stress multiplied by area. Now, the stress at a distance y, therefore, force will be given by stress y multiplied by area. So I have my stress force. Secondly, I shall look at the weight force at the bottom. Weight. Now, weight is given by mass times gravitational force, but again, mass is given by volume times density. That is volume multiplied by rho. Then, volume is given by area multiplied by height. Area times height. But in this scenario, my height is going to be y. Therefore, it will be area multiplied by y. So combine the three and I shall have weight is given by area multiplied by y multiplied by density multiplied by gravity. So with that, I have my two forces, due to stress, and that one due to weight. So after that, we know that upward forces is equals to downward forces. So the stress force is equal to the force due to weight. So that means stress y multiplied by a for this force is equal to the weight force a y rho g. So simplify that, area cancels out with area, and I'm left with stress y is equals to y rho g. Alright, now strain. The strain at a distance y will be given by stress at a distance y divided by Young's modulus. So I'm going to substitute this into that equation, and I shall have the stress y is given by y rho g divided by E. So this is going to form my first equation. Now, to get the second equation, we are going to consider this part that I've shaded, this small part, with the length dy. So assume that this part extends by delta. So it has an extension delta presented by that triangle, and its original length is dy. So that means the strain of this element, strain of y, that is the distance from the bottom, is going to be given by change in length divided by original length. So the change in length is the extension delta divided by original length, that is dy, and that is going to form my second equation. So I'm going to combine these two equations to give me a relation. So I'm going to combine the two equations. That is y rho g divided by E is equals to delta over dy. So make delta the subject of my formula, and I shall have delta is equals to y rho g divided by E times dy. Now, the delta represents the extension of a small element. So to get the extension of the whole bar, I'm going to be required to add, to sum up the small extensions. So how am I going to sum up? By integration. So the total extension, that is TE, will be given by integration of this small extension, that is from the limit 0 to the whole length L. L is the whole length. Then y rho g divided by E dy. Density, gravity, and Young's modulus are constant. So I'm going to write them in front of the integration sign. Rho g divided by E integrate L0 y dy. Now, integration of y with respect to y is going to give me y squared over 2. And I shall have rho g y squared divided by 2e. Then the limit from 0 to L. Don't forget those limits. So put in the limits. When I put in L, I shall have rho g L squared all over 2e. When I put in 0, anything multiplied by 0 is going to be 0, and therefore that is going to be my answer. So total extension is given by rho g multiplied by length squared all over 2e. And that is it. Thank you for watching the video. If there are any questions, kindly comment below. Thank you.